Today we're going to discuss some of the details of parallel programming in Python. And I say this using the broad category of parallel programming because we're going to discuss two different approaches, which you may be more familiar with one than the other, depending on your background. We're going to talk about threading, which we also discussed for Java, and so that may seem somewhat familiar to you in terms of this course. We're also going to talk about multiprocessing, so running multiple processes, where threads are usually seen as sort of smaller, almost smaller unit than a full process, and that have shared memory between them. Then processes are kind of more complete and larger conceptually. They are their own process. When you run a program on your computer, it typically is its own process and has its own independent memory. And we'll also show a bit about how you can communicate between processes when you do multiprocessing in Python. One of the beautiful things is, following again with that Python philosophy of there being one obvious and consistent way to do things, both of these two libraries, the threading library and the multiprocessing library, have a pretty similar style in terms of their interface and how you use them. So, basics of Python threading. You import the threading library and you need the thread class in particular. Here we've only imported thread because for now that's all we need. We define some function, and then to do very basic multi-threading, that's all you need, because you can create a thread with a function as one of its arguments, and then you can provide the parameters to that function, if it takes any parameters, and now you have a fully functional thread. So this is a little different than our Java setting because we're able to just pass a function, because again, functions are objects, so I can just pass them to the thread that I'm creating and say, this is what you're going to call. What will you call it with? These arguments. And then we create a second thread. Here we give it the same function, but with a different parameter. And then the two threads are going to print out different things some number of times. In fact, they'll print out each character from those strings. Now, just like we saw in Java, these characters as they are printed out may interleave. One thread may do its job completely and the other thread then does its job completely. It's not perfectly predictable. It's going to happen in whatever order a particular thread is given access to the CPU or to I/O buffers or different things like that. But the callable target that we are using here can access all the same memory space that it could have if it were called outside a thread. So just like if I called foo here. So if I had some global variables, foo's still going to be able to access them. If there are some shared objects that both versions of foo could access, they both can access them. And therefore we may have to do some synchronization, just like we've seen before. And then the start and join pieces probably look pretty familiar to the way that we did things in Java as well, the same basic concepts for threading there. We can also extend the thread class and write our own functions to sort of customize it a little bit. So I write a run function here that prints out my thread, and I can also override the init function so that I could provide this thread with some arguments in its constructor and be able to do things that way. The thing you have to be careful of if you are overriding init is that you also have to call to the thread constructor, the thread init, inside of there, or otherwise some of the basic thread stuff does not get set up properly. And it's also worth noting that you really should only override run and init. There are some other functions that threads have in Python, and you really don't want to be messing with those ones that give you an identifier for the thread, or things like join or stuff like that, that you really don't want to be messing with how those work, or your threads may not get along very well with other threads in Python. So here I create two myThread objects, and then I tell them to start and I tell them to join, and it would print out the myThread string once for each of them. In which order is not perfectly clear, and will they, sort of collide on how they print out? Also not perfectly clear, just as we usually expect with threading. And again, both of them would have access to whatever variables a class like this would have access to. So global variables or things like that, they would still have access to. Any shared static variables between the class, same thing. So there are some other built-in functions that may be useful to you in multi-threading in Python. You can get the count of how many threads are active and running, including the main thread of execution. So this should always be 1 at least, because your program itself is running in a thread that is the main default thread. There is a current thread function that you can get access to the thread that is active when current thread is called. So again, remember, we're not calling like t.currentThread. We are asking the system, who is the current thread that's running when I execute this function? And then the enumerate function that will return a list of all the active threads so that you can go through those. There are also some good built-in synchronization tools. I'm going to show you 2 of them, but there are others that are definitely worth checking out if you get further into multi-threading in Python. So these will be used for the same purposes that our synchronization was used in Java, to protect shared data, to make sure that things happen in a particular order that you want them to, that sort of thing. So the example I'm going to show here doesn't have multiple threads necessarily, and so it's not a perfect example of actually synchronizing, but it shows off some features of these synchronization objects, assuming that you already knew how to do, or why you would do some synchronization and what that could look like between multiple threads. So the lock class that's provided in threading, it has exactly 2 states. It is either locked or not locked, and that means even if the same thread enters a block in which it needs to acquire that lock, it will hang if it needed to acquire it a second time. So we have to be careful with the default lock to only be in structures of code where we need to acquire it once, and then we are sure we will release it again. So if, for instance, and by the way, you can use the with syntax for threads as well. So this is similar to the synchronized block in Java, that this is nice little shorthand to say, I am going to acquire the lock on L1, and when I exit this block, I will release the lock on L1, and so it will automatically do that stuff for you as a sort of shorthand here, and then you don't forget to release the lock. I also like these for the plain locks because they make it extra clear that you are within a locked space. You don't have to look for the release call. You look for when it stops being indented, and you know that's when the lock is released. But if, for example, I moved this with block up inside of the acquire and release space there, then on a regular lock, that would hang because it would have the lock already. The lock would be marked as locked, and then I would try to acquire it again when I hit the with, and the program would hang. So the other type of lock that you might want, it's got a little extra overhead to it. So if you're really looking for speed, then you might avoid it if you can. But that's the reentrant lock, or R lock. That lock behaves similar to the synchronization that we saw in Java, where if I try to reacquire a lock that I already have, then I'm safe and I can just pass right through that acquiring. So here we acquire lock 2 once, and then we ask to acquire lock 2 again, and that's just fine because it is a re-entrant lock. It allows you re-entry into locked spaces if you already hold that lock. Now you do have to make sure that you release it the right number of times because it will sort of keep count of how many times you are holding that lock. This is another good reason to use with blocks because you will automatically release it when you hit the end of that with block there, and you don't have to count the number of times that you've acquired and subsequently released it. So this is especially important when you have like functions that call to other functions that may have synchronized portions in them. A re-entrant lock can be very important there because you don't want to risk function 1 gaining the lock and then calling function 2, which also needs to gain that lock. In a re-entrant lock, that's fine. You already have the lock, so you can regain that lock, no problem. But with the standard 2-option lock, that could be an issue. But again, you've got extra overhead with the re-entrant, so you have to think about your performance needs there. There is another neat built-in class, timer, that is just a thread that waits some set amount of time before running whatever its callable target was. So here, for example, I set a timer to 30 seconds, and its action is whatever my logout function does. Now, you can do more complex examples than the one that's shown here, but this is just one example of setting up a timer and having it do a logout action, for instance, if it doesn't get interrupted. So that's the trick with the timer, is that you can cancel or interrupt it if it hasn't already reached its time limit and done its action by that point. So here we print out to the user that they need to press enter in 30 seconds or the session will time out. And then we start our timer and we wait on input from the user. If the user enters that input, we know they're still at the computer or whatever, and we cancel our logout timer. So you could imagine this being run every so often in a program where the user hasn't done anything for a while or something like that. So cancel, of course, can't do anything if the timer has already finished waiting and has already logged you out. The cancel there will just run right through that command and do nothing in that case where the timer has already hit its time limit and done its job. Okay, so why are we talking about two different approaches to parallel programming in Python? Well, it turns out that in the C implementation of Python, the standard Python that most people download and run, when you type Python on Agate, you are running a version of the Python interpreter that was written in C. And it is a garbage collected language, just like Java did garbage collection for you. And the scheme that it uses for garbage collection has this system to protect the memory that Python is using at any given time. It has what is called the global interpreter lock. This is a synchronization lock that protects the memory that the Python interpreter is managing for you and doing garbage collection on. So what it doesn't want to have happen is for some object to get dereferenced down to, being dead and by one thread, and then while the garbage collector is running, then that object gets re-referenced from somewhere else, and now should be alive, but the garbage collector has already marked it as dead and therefore deletes it while a reference to it is active, or that sort of thing. So essentially, this one lock needs to be held when you're changing references to objects, or you're creating new objects, or any of the sort of stuff that might impact garbage collection and memory management by the language. So only one thread can hold the global interpreter lock at a time, which means then that only one thread can execute Python bytecode at once, which essentially means that multi-threading, it doesn't really multi-thread the way that you would expect it to. There are some things that can be done independently, like when you ask for file input output and that's getting read into some buffer or that kind of thing. If you're doing library calls to other big libraries, like NumPy, Pygame. NumPy does statistics. Pygame helps, or has gaming related libraries. If you're doing network communication, sure, you can have a thread that's sleeping, waiting on some network response or that kind of thing. So there are still benefits to multi-threading in Python for some of these types of operations. But if you want to run things that are purely parallel, meaning that they are executing bytecode, they're hitting the CPU at the same time, because say you have multiple cores or that kind of thing, then adding this threading overhead of waiting on the global interpreter lock to be able to execute your code, it can actually make your program slower than if you just ran it in a single thread. So even though you say your machine has 4 cores and you want to be running 4 different threads that are each doing some of the work that needs done, you've got some big queue of data that you want to process through, and you want different threads handling different pieces of that data at once. Well, if they're all going to be doing lots of executing of bytecode and running pure Python code, then it can be slower. If they're doing stuff like file I/O or waiting on network communications or large-scale like video games graphics stuff, sure, maybe some of that can actually be offloaded to multiple threads. But for things that are actually executing in parallel, multiprocess can be the better solution. So again, to remind you, multiprocessing means that there is not shared memory. These are separate entire processes. They have their own memory spaces. And there are some other pieces of what a process means that they will get that single threads wouldn't necessarily get. But you can do communication between those processes. So you can have one process share information with another by sort of passing messages back and forth or passing pieces of data between different processes. And we'll see some examples of that. So we can get some of the behavior that you might have gotten familiar with if you've done multi-threaded things before by generating processes and then sharing information between them. So the multiprocessing library can be used for this. And here we're importing the process class. And again, the interface looks relatively similar. I write my foo function. It takes some arguments. It does a job. And I then spin off a process that will do foo with the argument test1 and another process that will do foo with the argument test2. I start them both. Why did I call them T1 instead of P1? I don't know, probably because I copied code from elsewhere, so be careful about that. But I start the two of them, and I ask, and then I wait for them to join, meaning waiting for them to finish their jobs, and it's the same basic outline. This is helpful because that means if you tried something with multi-threading, and it turns out it would actually be more effective as multiprocess, then some of the interface of how you set stuff up might still be transferable. The main difference will be that issue of shared memory. The two callable things here, the foos that I have fed here, they can only access their own arguments at first. Unless I pass some data to them, then they will have their own memory space and no access to any global variables or things like that. It has similar utility functions, being able to count the number of processes that are running in the system, get the current process that is executing when we run that function, and see how many active, or get the list of all active child processes from the main process that your program is running in. So to communicate between those processes, two examples of what we can do are a queue or a pipe. A queue functions like a normal queue. So the multiprocessing.queue is a multiprocessing.queue class functions like a normal queue, but objects can be put into or taken out of it between those processes. So here, for example, I've done a producer and consumer kind of model. One of them is putting data into the queue, and the other one is getting data out of the queue. And the producer gets the add function that I've written here that just puts the string new data into the queue. And the consumer gets the remove function that just prints out what it gets from the queue. And the arguments passed to them are the queue. So remember, I said that the processes will have access to their own arguments, and then anything that's created inside of their own process. Well, here they both have access to the queue as an object. And this is a particular kind of queue that can be handled across processes and used to communicate between processes. Otherwise, it would copy and give them only sort of new versions of data that's unique to them. So then I start the producer and start the consumer, meaning the producer would add data, the consumer would get data from the queue and print it, and then they both would finish their jobs and join. So that's one way that we could pass information between, is this sort of buffer or queue that feeds information between the processes. Another way is we can use a pipe. It gives two objects. Each one is sort of an end of the pipe, sort of like standard in and standard out, that there's sort of an input and output end for both sides. Not too dissimilar from when we did sockets and how each end of the socket gets to send or receive information from their end. So we've got one end of the pipe and then the process pipe. So the main pipe, I've called it here, and the sub-process pipe. So my main process is running. I haven't created two processes here because remember, my program itself is running in the main process. So I create a new sub-process. I give it write as its function, which sends new data and the array 1, 2, 3. And its arguments will be the pipe that it's going to be sending over. And then my main function, or my main process, is going to be asking if the pipe has information. While the pipe has information, then it will get that information from the sub-process and it will print it out, whatever is received. So you've got send and receive. Both of them could send and receive, but in this example, I'm only using the main pipe to receive and the sub-process's pipe to send. So I could send information back and forth across that pipe if I wanted to. And you'll notice again, similar to what our sockets were doing with their object writing streams and object reading streams in Java, this pipe is sending data across as the object type that it is, and the other end of the pipe will receive that data as the object type that it is. So this string would come across as a string, and this list would come across as a list. And so it's able to send data, because it's all being done natively within Python, it's able to send and receive that data as the type that it originally was. Now, there are more ways to communicate between processes that you could certainly work with. These are just two of the main ways that are provided in the subprocessing module. There is the shared C types. If you want to be able to share C-based types of data across multiple processes, there are managers for managing threads. There are process pools that you can create that get access to things together. And similarly for doing multiprocessing on a cluster of machines, there are libraries for that in Python. And for doing parallel programming on GPUs, there are libraries for that as well in Python that you might check out if those are features that are of interest to you. So we saw that in Python, there are two main libraries for doing parallel programming, one for threading with shared memory, and one for multiprocessing with communication between the processes rather than shared memory. And we also saw that Python kind of nudges us in one direction or the other, depending on the type of parallel programming that we're going to do, because multi-threading will be a little weaker, and it will be especially weaker if in Python we are executing bytecode, native Python code, in multiple threads at the same time, because they have to get access to the global interpreter lock, which protects the shared memory and the memory management in the interpreter there. So some simple libraries in terms of interface with hopefully some familiar structures to them in a sort of unique and Python way, and with their own benefits and complications that we looked at together.